Are a type of classification algorithm. If you have watched the rest of my videos, I think at this stage you should have a pretty good idea what this means. But basically, it's a way for machines to try to figure out what something is based on what it knows about everything else. Let's start with some jargon. This line is a one-dimensional space. Here you can go left or right. If I add another dimension perpendicular to this, I get two-dimensional space, which means I can still move around in the same one-dimensional space I did before, but I can also jump into another version of that space that exists perpendicular to that, so I can move left, right, up or down. If I create a dimension perpendicular to these, I get three-dimensional space, where I have all the powers the two-dimensional me had in the one-dimensional space, except this time I can move around in 3 dimensions. So I can go up, down, left, right, in or out. Now it's usually about here where it gets really hard for me to draw dimensions perpendicular to three-dimensional space. I might be able to show it to you like this maybe, by just letting time pass and get away with it. Now, but all joking aside, this is just a fun way of thinking about this, so just hold these concepts in your head for now. I think it will give you an interesting perspective later on. So the first thing you need to know about is a hyperplane. The hyperplane is basically a type of border separation that divides a space, and it's always one-dimensional less than the total space we're in. So you can see here in this two-dimensional space, I have a one-dimensional line as our hyperplane. On the other hand, if we have a space of 3 dimensions and we need a hyperplane that's 1 dimension less than this, our hyperplane needs to be in 2 dimensions, and it kind of looks like this, a flat plane, kind of like a wall. Let's look at our car dealership again, with price and blueness being our features and our class being if they sold or not. So we're going to graph this in 2-dimensional space. And let's say I have some arbitrary yet suspiciously convenient data scattered through my graph. The support vector machine will try to linearly separate the data here with a 1-dimensional plane. And to do this, it tries to create a hyperplane that gives the best separation of the data on the graph. Now there are many different lines we can draw that separates this data, but we want to find the one that gives us the most space on either side so that we don't misclassify other points that may come along after. Think about it like this. If you want to separate things, you create a border. And the best way to create an accurate border is to find the differently classed points that lie close to each other and create your line there. These points that are used to create the borders are called the support vectors. We want to have the largest margin between these two borders possible that separates our classes, and that's what determines our final hyperplane. Now the reason we go to all this bother in creating this hyperplane is so that when we get a new point, we can tell what kind of class it is based on what side of this line it's on. Now, over the past couple of 100 years, mathematicians have discovered, much to their dissatisfaction, that data doesn't always follow such perfect scenarios where these things will always be over here and those things will always be over there. One trick to solve this is using a soft margin, which is basically a way for us to ignore stragglers in our data that might cause our model not to work. So instead of drawing the line like this, we draw one like this. Like we literally cut our model some slack and we say, okay, I'm going to try and draw a line that fits despite a few points that don't really conform to everything else. This gives the final calculation an error margin. What about data like this where there's no way to linearly separate it? To get around this, support vector machines do what's called a kernel trick. A kernel is basically what's called a mapping function. This means you pass in something and it transforms it to something else. In our case, we want our kernel to transform a 2-dimensional object into a 3-dimensional representation. A simple example of a kernel is using the dot products. For example, let's say we have a point x and its values are 3, 2. We can transform this by giving it the value 3, 2, 2 squared plus 3 squared. So that makes it 3, 2, 13. Now by using the products of the values that make up the 2-dimensional point, we can give it a 3-dimensional representation. We have a few types of kernels to choose from because depending on the data we have, we may need to adjust how we calculate the kernel. Let me show you an example of what a kernel will look like. See, different kernels can have different shapes. For example, a Gaussian kernel may look like this, but this doesn't really do it justice, so let's try this. Let's say we have our 2-dimensional point like this, not linearly separable. Notice how I take the 3-dimensional space and fold it so that we can separate the representation of our 2-dimensional objects. And by adjusting the sigma, we can vary the shape of the hyperplane to fit our data. So how do we do this? Well, let's take a quick deep dive into some of the maths. I can describe any point here using 2 coordinates, x1, x2, e.g. 3, 2. Think of the vector of x1, x2 as being the direction from 0, 0 to that point. So for example, the vector here will look like 3 over 2. I can describe a line on this graph by saying it's perpendicular or at a right angle of a vector like this. I can also describe the magnitude of a vector or how long the distance it has to get to the point as the square between x1 and x2. In our case, it's 3 squared plus 2 squared which is 9 plus 3, which is square root of 13, or 3.6. Lots of numbers after that. I can describe my hyperplane with the formula W transpose x plus b equals 0, where W is the vector that describes a line, x is the class, and b is the offset. So as W changes, my line changes like this. And when the offset b changes, my line does this. If I have a 0.66 as a positive class and 3,2 as a negative class, how do I solve this? Well, I can create two hyperplanes to mark the borders of each point. You can see 6x plus 6y plus b equals 1 because it's positive, and 3x plus 4y plus b equals minus 1. And what I'm looking for is a w1x plus w2y plus b equals 0. In other words, the hyperplane that will give me the best separation of this data. And to do this, I need to identify the vector that passes through the other two hyperplanes. So if I plot this hyperplane, it's going to be 6 over 25x plus 8 over 25y plus minus 59 over 25 equals 0. And it looks like this. And you can see it nicely separates our 2 points evenly. Now if I get a new point like 7, 7 and I plug it into this formula, then depending on what side of the 0 it's on makes it that class. So that's pretty much an introduction into support vector machines. Now if you want, I can do an example of the math in more detail in another video, but I think this will give you a basic understanding of how they work.